So yesterday, the relationship that we talked about was the mole mass relationship, where we can use conversion factors of grams per mole or moles per grams. And we could calculate the number of grams in a mole of a particular substance, or we could calculate the number of moles of a particular substance. And that's what our homework was yesterday. Today, what we're going to do is we're going to talk about the mole volume relationship. The mole volume relationship right there. Unlike liquids and solids, the volumes of moles of gas measured under the same physical conditions are much more predictable than the solids and liquids, okay? Here we go back to Avogadro again. Mr. Avogadro was a very smart guy. And, I'm sorry, just... Avogadro's hypothesis states, equal volumes of gas at the same temperature and pressure contain equal number of particles, okay? Regardless of what gas it is, if it has 10 particles, it'll have the same volume as another type of gas that has 10 particles. If the temperature and pressure are the same, then the volume of 1 mole of any kind of gas is the same. Let's look at that again. These little blue particles here are really much smaller than these red particles here. Okay, but if I have the same number of blue particles as red particles, then they will occupy the same volume if they're at the same temperature and pressure. Now I said standard temperature and pressure. Standard temperature and pressure, the temperature equals 0 degrees Celsius, and the pressure equals 1 atmosphere, which is the normal atmospheric pressure at sea level on Earth. So back to this hypothesis, the volume of a gas varies with change in temperature or pressure. So due to those variations, we have to set the temperature and pressure, like I just said, at standard temperature and pressure. 0 degrees C and 1 atmosphere, okay? And drum roll, here's his big hypothesis. This is the idea. At the standard temperature and pressure, 1 mole, or 6.02 times 10 to the 23 represented particles of any gas, of any type, has a volume of 22.4 liters. And we call that the molar volume of gas, okay? So, spoiler alert, if we know that 1 mole equals 22.4 liters, we're talking about gases, we can make 2 conversion factors out of this, just like we did with the molar mass. What's one of the conversion factors? Divide both sides by 22.4, you get 1 mole over 22.4 liters equals 1. The other conversion factor would be 22.4 liters over 1 mole. And we can use these conversion factors just like we used the molar mass to convert from volume to moles or from moles to volume. Here's the same thing I just said, but it's typed. There are your 2 conversion factors right there. And remember, this is at standard temperature and pressure. 22.4 liters of a gas is 1 mole. Here's a practice problem. I suspect this is practice problem in just a second. 10.7, sulfur dioxide. Indeed it is. Sulfur dioxide is a gas produced by burning coal. It's an air pollutant and one of the causes of acid rain. Determine the volume in liters of 0.6 moles of sulfur dioxide at standard temperature and pressure. Okay? So what we're given is 0.60 moles of sulfur dioxide. I'm going to put that over 1 just so I remember that I'm multiplying fractions. And from our previous slide, we know that 22, right here, 0.4 liters over 1 mole is equivalent to 1. That's our conversion factor. So all we have to do is put 22.4 liters of any gas over 1 mole, and the gas we're talking about is SO2. Moles of SO2 cancel, And we're left with liters as our units. And that would be, let's see, is that 13? I'm going to have to get my glasses out. And what are the correct number of significant figures? Two significant figures. And here we go. Okay, I'm also going to work for an example, problem 20 in the book. I'm just going to do A, though. What is the volume of the following gases at standard temperatures and pressures? And the first is 3.20 times 10 to the negative third moles of CO2. And they want me to tell them the volume in liters. So I have to multiply it by conversion factor. What's the unit on the top of the conversion factor? It's going to be liters. And what's going to be on the bottom so that moles of CO2 cancels out? Moles of CO2. At standard temperature and pressure, how many liters is 1 mole of CO2? How many liters? It's always 22.4. You will know two numbers when you're finished with Avogadro's hypotheses. The first number will be 6.02 times 10 to the 23rd particles per mole. And the second one is right here, 22.4 liters per mole. That was number A. Number B and C for 20 are exactly the same. So go ahead and work those after I show you how to work 21A, which is very similar to B and C. So once you know how to work 21A, you'll be able to do this. At standard temperature and pressure, how many moles are there in 67.2 liters of SO2? 67.2 liters of SO2 gas. I'm putting it over 1 so I can remember that it's an equation. And I have liters on top. I want to get moles as my answer. So on my conversion factor, going back to the conversion factors, which one of these two am I going to use? Going back, the question was, if I want to get moles as my units of answer and I'm starting with liters, which conversion factor do I have to use here so that liters cancels? Put liters on the bottom, exactly. 22, what's that number? 0.4 liters on the bottom, and what goes on top? 1 mole. Liters of SO2, this is SO2, cancel, and I'm left with moles. All I have to do is divide 67.2 by 22.4, and I believe it's 3.0. How many significant figures should I have? Oh, probably should have 3. That has 3. This has 3. So it's 3.00 moles. B and C for 20 and B and C for 21 are almost identical. Okay, so I just got some input that this was 3.2. And what's our answer going to be over here? The key is how we set it up, though. It's going to be 7.17 times 10 to the negative second. That's not really how I want to do it. All right, closing the loop here. 0.717 liters. 3 significant figures, just like this number and this number. So another thing about the mole to volume relationship is that you can calculate molar mass and or density using it. The density of a gas is standard temperature and pressure, and the molar volume can be used to calculate the molar mass of the gas. How does that work? Well, if we have a density, that would mean we have grams over liters. And if we multiply that by 22.4 liters per 1 mole, which is the conversion factor that we just learned, and this is density right here, density, when the liters cancel, we're going to get grams per mole, which is our molar mass. Okay, see how that works? And conversely, if I have grams per mole, which is the molar mass, say for water it's 18, and I multiply that by moles, 1 mole, over 22.4 liters, then moles cancel, and I will be left with grams per liter. Once I actually divide whatever this coefficient is, my number of grams, by 24, I'll be left with grams per liter. Grams per liter is, what are we measuring when we measure gram per liter? That's a density measurement. So, using this volume, we can get back and forth between density and molar mass. Or we can go from molar mass to density. Okay? And to do that, here's an example. The density of a gaseous compound containing carbon and oxygen is found to be 1.964. That's a density right there, grams per liter. That's under standard temperature and pressure. If I take that density, 1.964 grams over liters, and I want to find the molar mass, I know that molar mass units are grams per 1 mole, or grams per mole. I can multiply my density by 22.4 liters per 1 mole. Now my liters cancel, and if I multiply 1.964 grams times 22.4, I will get the molar mass of what this compound is. How many significant digits should we have in our answer? This one's got 4 significant figures here. This one has 3. Our answer should have the same as the lowest number of significant figures, 3. And I got 43.9936. If I round that, I get 44.0. I suspect, I don't know this. Oh wait, they did tell us. Carbon and oxygen. And it weighs 44 grams per mole. My guess is this is CO2. To tie this whole chapter together, or this whole section together, I want to show you this. This little chart right here shows the mass relationship, the volume relationship, and the mole relationship. If you know moles, using our little equation, our little conversion factors, if I give you a number of particles, you can use 6.02 times 10 to the 23rd to calculate how many moles, okay? If you know how many moles of something you have, you can calculate the volume using 22.4 liters per mole. That's right here. Or you can calculate the mass, knowing the molar mass, grams per mole, okay? If I give you the mass, you can calculate the number of moles, and then you could calculate representative particle number or volume. If I gave you the volume, you could use moles to calculate mass or representative particles, okay? That chart right there is something you need to get in your brain, because that is how we do all these mole calculations. It shows all 3, and if you look real close, it's in your book. If you look at all 3, right here, and right here, and right here are the actual conversion factors, okay? So that'll help you. It's like a road map. This road map will tell you how to get from mass to volume through the mole. And you know what I like to think of this mole as? Is anybody ever been on a traffic circle? Roundabout? That's kind of what this mole is. You're driving here. You want to get over here. You have to go through the traffic circle to go this way. Or you could go to the traffic circle and go this way. And the traffic going this way can go here or here. Make sense? Those are just mathematical relationships. Come on.